Hi, this is Paul again. I've got something new and interesting to show you again. Last year, I made a useful discovery. I found that by using rings of 40 colored balls and using 4 different colors, I was getting amazing results with 3D geometry. The first thing I tried was the 3D geometry of a pineapple. I first came up with the idea of using 4 different colored balls is when I started experimenting with the phi spiral at 137.5 degrees. What I found is that when I was using NURB curves, the gap between the 2 vertices were too great and I was getting a big sag in the middle. I needed another vertex around about the midpoint, so I decided to start designing a little machine to provide 2 vertex points for each 137.5 turn. I guess mathematicians don't really need more than one angle. They just need the 137.5. But I do all my work in 3D reality, so I guess I was only looking for a practical solution. But I guess this practical solution of mine started producing some amazing results. Anyways, I called this new discovery of mine Quad Step Phyllotaxis. Okay, let's focus on A-DNA first. They show the Atype DNA as being a diameter of 23 Angstroms. I'm working in millimeters, so I make it 230 Angstroms. I show that we have a stack of 5 quad step 48 ball rings. Now if you look at the very start of the cyan helix, you can see that it starts with the cyan ball and then it goes to a red ball. This is 37.5 degrees. Now the red ball goes to a red ball and that's 30 degrees. Now this goes to another red ball and that's another 30 degrees. Now we end up with the red ball going to a yellow ball and that's another 37.5 degrees. Now 230 degrees and 237.5 degrees comes to a total of 135 degrees. Now if we multiply by 3, it comes to 405 degrees. So this is where the 11 rungs come from, because 12 rungs take you to 405 degrees. Now if you look halfway between the rungs, you see a Plato cube between 2 red rungs. Now the long diagonal of this Plato cube comes to 40.864, but that is the distance between 2 rungs of A-type DNA. So what we have is the distance which they call axial rise of 20.432. Now in the book it would be 26, they show 26 or 0.26 for their Angstroms. I would say that using this 3D Platonic order is much more accurate. The book shows a twist angle of 33 degrees. But I show this in a lot more detail. I show it's 135 degrees in 4 different angles. Okay, let's have a look at the B-DNA. Now if you look at the bottom of the B-DNA, I'm showing a size 6 icosa. Now if you look, I'm showing a string of 6 size 1 icosas going from the face of the icosa, the center point of the face, to the center point of the opposite face. Now you can also see that this string of icosas are sloping. That's the way the geometry is. Now I've been checking the diameter of this arrangement, and to get the diameter as shown in the book, I needed to add another icosita either side. Oh, by the way, I call a size 1 icosa an icosita. That's the smallest icosa you can get. I realize if you want to be impressive like the scholars, you have to use Latin words. It's a lot more posh. Okay, the distance between the top and bottom vertex of the icosita is 34.0 0.271. Now the book says it's 3.4 Angstroms, so something must be right. Now the book says that the diameter is 20 Angstroms. Now I am showing a diameter of 213. That's the best I can do. And that is going to be 21.3 Angstroms. Now the set of 8 icosas, size 1 icosas, are sloping. And this is along a vector. This slopes along a vector. Now I show some of this in my videos about 5 rectangles. The rectangles can be split into smaller rectangles. So this is how you more or less can get the sloping vector to go as a zigzag. Now this is the only way that I could get a double distance on a rung to cut it down by half to match what the book says. Now all the geometry that I'm using are matching the dodeca, because I give the dodeca a diameter of 230. So the icosa is related to that diameter. There's something I'd like to add. All the geometry of bead DNA seem to line up on the red balls. Now the 40 balls are all 9 degrees apart. So 4 balls gives you 36, and that gives us the red balls. So I guess the red balls are giving us a wonderful 5-sided symmetry. Isn't that something? Okay, now we can focus on the third type of DNA, and that will be the Z-type DNA. Well, to tell you the truth, I almost give up on this one. I was so close and so far away all the time. But I finally cracked it, and it is quite simple. Actually, it's very much like the A DNA. We have 3 vectors 120 degrees apart, and we've got another 3 vectors that follow them 44.6 degrees apart, just like on the dodeca. Actually, I didn't realize this was the same on the icosa as the dodeca, with 44.6 and 75.4 degrees, the golden ratio. Exactly the same. I think this is what happens about sacred geometry. Everything is very simple, and it's basically like a puzzle. There's always a simple way to work it out. I think this is where the quad step rings come in on its own. Because when you have a stack of half a dozen rings, it's like a cylinder, and you can just like wrap the helix around the cylinder, just like a piece of cord, you can wrap it around the cylinder. So it comes in on its own. Now that is why this helix I'm showing looks a lot better than what the scholars show. What the scholar shows looks very awkward. Actually, this is what led me down the garden path. So you can do a comparison by yourself. My helix looks a lot more smoother than the Z-DNA that the scholars show. Okay, the diameter of the Z-DNA works out at 180, exactly the same as what the scholars say. They show 18 Angstroms. And the actual rise, or the rung gap, is 40.658. This is exactly double that of ADNA, because it's very similar. You can see this, I put a Plato cube and it takes up 1 gap. And on the ADNA, it takes up 2 gaps. Now the scholars show this gap as 45. And I show it just under 41. So anyway, I've shown you the 3 types of DNA and what my Platonic order and my quad step rings can do. But when you take a Google search on chaos, I've seen it up to about 80 million results. So I guess most people go with the flow. This is what the scholars say, and this is what they want. So I'm going to call it a day now. And so this is Paul saying thank you very much for watching my video.